show you some an interesting trick that might appear sometimes when it comes to formulating DPs on tree. In n squared. The problem at hand, and I will leave you like some minutes to think about. I think is the following. So initially we are given a function, basically p of I, or let's call it c of I, which means that we have an election for n people, and the ith person wants to vote with the ci person. So basically, we know for each person what their preference of voting is. Whenever we are given such a construction where we know that I points to some function of I, and this is from 1 to the same n, they go from the same span, it's called the functional graph. Oh my god. Functional graph. And it has the following properties. So they generally look like trees, but with one small caveat that in each component, each weakly connected component, there is some cycle, and then there are some arborescences spanning from each of the nodes from that cycle downwards. Okay, that is off bounds, I guess. Is that clear for everyone? Why that happens? Okay, so we are given such a functional graph, that is, we know for each person I that they want to vote with CI. But we want to establish some chaos in this election. And for that, we can eliminate up to k candidates from participating, which means that, for example, if we are to disallow this person from participating, that these three people will have to, they can no longer vote with this person. We are then introduced to two cases. One, when we eliminate A was already voting for some B, and B was different from A. In such a case, for every voted A, we now establish that C will vote B. I remind this is the problem statement. This is not an explanation or whatever. This is a problem statement. Or otherwise, in the second case, when A was voting with themselves or were undecided, then every voter of A becomes undecided. Is the problem statement clear for everyone? Wait, I have to open the chat to actually see. What is the problem about? So we're given such a functional graph, and we know that we are also given a k, but not really. Assume there is a k, and we know that we can eliminate k people from the electoral process. When we eliminate a person, it means that people can no longer vote with that person. And there are some rules as to how people revote based on the fact that, based on the information that some person no longer is in the race. In the case when that person was voting with someone, all of its followers will now vote with that person. But in the case where that person was voting for themselves or was undecided, upon elimination, all of its followers will now become undecided. and they are called undecided. The problem is that for every single k, for every count of people that we can erase from the graph, what is the maximum amount of people that we can get to be undecided after eliminating k people? So for every k from 1 to n. I feel like maybe I should give an example uh, to explain the problem better. So assume that this is the functional graph that we are given at input. We know that I votes with ci, and the edge is from I to that uh, candidate. Let's say that we want to eliminate this person, this person, this person, this person, this person, this person, and this person. Okay, we eliminated kind of too many people. Let's leave it at that. Okay, then let's see now how many people become undecided based on this fact. So for this person, they would vote with whomever the eliminated person would vote, but they would vote with anyone that their leader would vote, and their leader is eliminated. Then that leader is eliminated. That leader is eliminated. That means that they have to vote themselves, but they are eliminated, so they are undecided. So that means that this person is also undecided. All of the people from the cycle are then basically undecided, and all of the followers of the people from the cycle are undecided, except for these two people, which can still vote for their leader because their leader is not out of contention. Is it a bit more clear now? I should maybe try to uh, share the task. No, it's not clear. Oh my god. Oh no. Okay. I'll just abridge the problem statement until I give it to you. But basically, we have a functional graph. We have to eliminate uh, a number of nodes from this graph. Assume that it's mostly like a tree. So that after we eliminate, wait, no, that's not really it. A lot of things stem from the problem, from the statement of the problem. This is the problem statement, but it's not yet translated, unfortunately. It's not this one. God damn it. No, it's not this one. Oh God. There are multiple problems called politics. So I'll reiterate in the meantime. So this is the problem. This one. So we are given a. We know that there are n people and they want to hold an election. We know that initially the minds of every person is made up. We know that person I will vote with person CI. But we also know that we can eliminate up to uh, up to k people. Let's say for some value of k, we can eliminate up to k people and forbid them from being voted, from belonging to the electoral process. When we do so, let's say that we eliminate person X. Then some things will happen because obviously, if we do not allow any person to vote with X, then some these people have to vote with someone else. Then the following rules apply. If at the time of elimination X was voting with Y and Y was not X was not voting for themselves, which is perfectly allowed, then every follower of X, everyone that would normally vote with X, they now instead vote with Y. So they vote with whomever X wanted to vote with initially. Then, if X would vote for themselves, yeah, I'm just repeating the statement right now. If X were to vote with themselves, then for every individual I who would vote with X, they would now be undecided. And similarly, if X is undecided, then every follower of X will also become undecided. We want, given this value k of how many people we can eliminate, to know what is, after eliminating k such people, the maximum number of people that can be undecided after such a process. So, for example, if this was the way people voted, so 3 would vote for 2, 2 would vote for 1, and 1 would vote for themselves. If, okay, let's say also 4 would vote for 2, and I know 5 would vote for 3 or something. Then, if we are to eliminate 1 from the voting process, then it is said that 1 will become undecided, 2 will also become undecided, but 4, 3, and 5 will not become undecided because 3 can still vote for 2 because they still are in the election. 4 can still vote for 2. 5 can still vote for 3. Yeah. I'll leave some more minutes for you to think about the problem until 15:46. It took too much time, unfortunately. I'm sorry for that. Uh, what you are saying, Timur, is technically wrong because you do not have to eliminate a whole graph to have people undecided. You can eliminate just some nodes of any weakly connected component. And when you do so, some people also become undecided, just as I've shown in this case. Uh, yeah, well, one firstly needs to eliminate the cycles, so that's clear. But for some components, we might not touch them at all. But then we can just remove some nodes partially of the component. We do not have to eliminate to erase every single node of the component to get people uh, undecided. In this case, we just eliminated the root basically, and now we have two people that are undecided. Yeah. So obviously, a first step is to eliminate the cycles. No, one actually needs to eliminate the entire cycle. So let's analyze on what happens when we uh, eliminate people. So firstly, consider the structure of a functional graph, which, as I said, is formed of a cycle, and then some trees spanning downwards from them. If we are to eliminate any one person from the race, like let's say we eliminate this person over here, then maybe they become undecided. I think they are technically undecided because they are eliminated. Yeah, they are considered decided if they are not eliminated. Okay. Um, but every other person can just skip them on the chain. So then the issue on when a person becomes undecided is if I keep skipping, they will get back to themselves or not really. That is, they don't really go back to themselves, but they go back um, to a person that has already been eliminated. Is the issue because a person voting themselves is fine, but a person going in a cycle up to getting back again to a person that has already been eliminated means undecided. Okay, so then to be able to generate such a cycle that any person would vote for, um, uh, okay, to be able to generate such a cycle where a person would go through this cycle back to voting a person that is undecided, we conclude that we need to eliminate everyone from the cycle of any weakly connected component to start making some progress. Stop for a while. Okay, I will stop. Is the issue that the did people not have enough time to read the statement? Because I can take more time. Oh, okay, sorry. Okay, then I'll come back at 15:55. Okay, okay. I'll take a break. Uh, uh, Ping me when you're ready, I guess. Wait, someone raised a hand. Oh, why did I not hear that? Uh, okay. So we can start. Uh, is is the problem statement clear? Because I uh, understand why it might be a bit too convoluted. It's clear. Hooray! Okay. So then, as I've explained earlier, uh, to start getting any people, any person from any weakly connected component to be undecided, we need to first eliminate the cycle of that connected component. Does everyone agree with that? Yeah. Okay. But then the issue is, like, can we eliminate more? And what would happen if we eliminate more? Now we can reduce the problem to a simple tree because the cycle is eliminated. We don't really care that it's a cycle. Uh, like this entire subtree could have moved. This entire subtree, for example, could have not point to this node in particular, but maybe this node, and the result would have been the same. So assume that the given graph is a tree. Then what we know is that all the children of the root are now undecided, but we can also eliminate any further child of uh, the root to get more people to be undecided. And then after eliminating those people, we get more people to be undecided. So essentially, what happens, the only way that it would make sense to eliminate people is to not eliminate like a random node from the tree. Because if that is the case, maybe we can just jump it. We need to have a connected chain of people, uh, of undecided people. That is, eliminated people, every eliminated person needs to be connected by more eliminated people up to the root. And then, after selecting what essentially is such a partial subtree of the graph, all the children, well, also the nodes, but all the children of those eliminated nodes become undecided. Is that also clear? Hooray. Okay. So, what do we have by the end is we uh, the issue is the following: how do we solve this problem? So we know that by eliminating a node, we get basic. We increase by the degree of the node. Well, maybe -1 because we do. The father should have already been undecided, but we increase by a value like this. Normally, greedy would work if for any node we would have a cost to eliminate this value, and let's say this cost would be +7, and then the cost of any node in the subtree would have to be greater than 7. If that were the case, we can apply greedy because every single move that we would make uh, should be optimal for the current reasons. Well, actually, no, 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 no. If no, sorry, if they are less than 7, if they are less than 7, then we can apply greedy because we know that if 7 is currently the best move that we could do, and for example, we might have some other node that we might want to eliminate, but this yields a cost of +5, then we know that after if we were to first eliminate 5 and then get the 7, And after eliminating the +5, we only get like the options to +3 or +2 or +4, anything less than 5. And then if we continue downwards with these, then we start getting diminishing returns. We get moves that become increasingly worse. Whereas we could just right now eliminate this node and get +7 undecided nodes, and then it would be great. If that were the case, we could do a grid, but we can't because it isn't the case. Is that clear? Why greedy doesn't work? Uh, if so, then this is a pretty bad thing to do when teaching informatics, I think. But if it's not greedy, then it has to be DP. uh, this is not a rule, this is a bad rule. But I just want to point out that by now we should try to consider DP. Maybe you have seen that n is up to 1000. So we should expect that we will have a DP of 2 parameters. Probably, very likely, one of the parameters will be node. So we exhausted one parameter. But also because the problem asks us to how we converted functional graph into a tree. So as I said initially, if we look at a functional graph, it starts with a cycle. How do I increase? Oh, yeah, let's go. Okay, it starts as a cycle. It has a cycle in the beginning. But if on this graph we do not erase, if we randomly erase nodes, like we erase this node here, erase this node here, then the only nodes that become undecided are those that we eliminated, because every other node can just skip it based on the rules. So then, to make any progress, we need to first eliminate the entire cycle. And because we eliminate the entire cycle, we can just compress the cycle to a single node, because we do not care that uh, uh, we do not care of the relative orders of the subtrees, given that basically all the children of any node on the cycle are now undecided as well. So then we can just assume that we compressed the entire cycle into a single node. Well, technically it isn't a forest, but yeah, we will basically solve the problem for the forests. For the forest that ensue. We don't need to really think of them as forests, but because there might be multiple such components, connected components, yeah, there will be multiple such trees. So yeah, we reduce the problem from a functional graph to solving multiple forests. And now we notice that we basically have the following operation. So we start with a node with the root that is eliminated. And now all the other children are eliminated. But then we have to make a choice of which of the children we uh, invalidate further. We eliminate them. And each child, if eliminated, uh, would bring about some new nodes that will be undecided, particularly its children. So then we have a set of augmentations that we can do. Initially, it's the set of all the children. And each augmentation comes with a cost. And we want to do k augmentations to increase our final cost. Okay, good. Then those, after eliminating those values, we also get more options downwards of augmentations that we can do. So for example, this node, when we eliminate, we introduce, I've said, for example, 7 new undecided children, because they would have to vote with this person, which would have to vote with this person, which is undecided. So then this person is undecided. So then they are also undecided. And I've said that technically a greedy approach where we try to eliminate the best solution ever will it might not work for the reason that if we eliminate the best cost now, we did the best solution for k equals 2 because we eliminated the root and the node. But then for k equals 3, it might have been the case that it made sense to eliminate some other sibling and then eliminate some other child of that sibling. And after we do so, we might get a cost of plus 5 initially, which is worse than the plus 7 that we would have for the first node. But then we might get some plus 4 from one of the childs, whereas in the original node, we'd have plus 7. But all the 7 children might bring about just an augmentation of plus 1. So then greedy shouldn't work. So we should try DP. Is it sort of clear by now? What the problem asks and what we should try to solve, really? That is what we will do. We will do DPs on subtrees. And we will try to do so in n squared time. And by the end, it will be a very anticlimactic end, unfortunately, but I think you should know about this trick, lest you might uh, see it when some other time when you should solve it, really. So we have DP of node. We want to solve by DP. So obviously, a first parameter that we should do is to fix the node. So we exhausted 1000. We can technically afford just one more parameter. And because the problem asks us to solve for every count of eliminated people, we should add another parameter here called count of eliminated, but I will abbreviate as lowercase k, which should then mean assume that uh, the parent, uh, the parents of the node and all of its ancestors are eliminated. So now I should be audible. Do you still hear me now? I hope you do. It seems like you do. Okay, so as Timur pointed out, no, because 3, for example, can still vote for 2. 2 is still in the election. So then 3 could just vote 2. They are allowed to. It's not forbidden by the laws of the election. But 2 would vote for 1, and 1 is out of the race. So then 2 cannot get any more indications from 1. 1 would vote for 1. 1 would vote for himself. So then, yeah, that's it. This is why it matters that if we have like basically a tree structure, assume that the root votes for themselves, that we only eliminate a partial subtree of this. We might eliminate a partial subtree. So we not kill, but eliminate all those people. And then the undecideds are all the children of the eliminated nodes. So then basically, because of the way that this extension happens, we expect that we basically have a set S of augmentations, which mean that if we eliminate any one of these children to expand our eliminated subtree, we would get an extra, I don't know, some number of new undecided people, because we invalidate their direct parent. And this set of selections that we can do to increase our count of eliminated nodes follows the tree structure. We keep going downward, and we get more options out of that. And I said to solve this, we should employ a dynamic programming. Because we have n up to 1000, we expect maybe we should only have 2 parameters. One of the parameters should be node, and one of the parameters should be the count of eliminated nodes, because we need to answer for every single count of eliminated nodes, because that's what the problem asks. So then in the root, we should have like answers for all the k's from all the counts of eliminated people from 1 to n. So maybe we should try to calculate this value for every single subtree. And then the natural DP definition follows. Now, assume that for this node, all the nodes from it up to the parent are eliminated. That is to say that initially this node, for which we calculate the DP, has all of its children undecided without any further movement. If we were to eliminate k more things from the subtree, what is the maximum count of undecided nodes from the subtree? So the definition is clear, no? Oh my god, I can do 5. It wasn't the case before that one could do 5. Okay, so we have DP node k equals max count of undecided. I expect the transition to be somewhat natural. Assume that we have sons of the node S1, S2, ST. So these are all the children of node. Then if we eliminate a total of k values from the subtree, we expect to attribute every single one of these some other count of how many nodes are eliminated from their subtree specifically. So this might be like k1, k2, kt. And if that is the case, because we also eliminate node, this sum has to be equal to k minus 1 plus 1 for the node equals the final k. And the dp value that would ensue from this would be dp of S1 and K1, because we calculate what is the maximum number of undecided nodes if we just eliminate, as we've said, K1 nodes from S1 plus dp of S2 from K2 plus dp of ST KT. And we have to take the maximum of this over all partitions K1, K2, KT, which I've told you is like, technically speaking, around K choose, well, it will be K plus T choose T, around this value, which is exponential, which is bad, obviously. But we agree that this would be a transition for the DP. No? Although it's exponential currently. Are there any questions? Okay. To simplify all of this, let's assume that t equals 2, because if t equals 2, we have a very fortunate case when we really have to fix two values, k1 and k2. And because they both go up to k, it will be like O of n squared. Whatever. It won't be O of n squared, is the joke, in fact. So we'd have like for k1, no, initially for k, actually. Okay, no. Then for k1 from 1 to this k, k2 becomes k minus k1, minus 1 actually. And you would say that dp of node of k is it changes to the maximum of whatever we had before, and dp of S1 k1 plus dp of S2 and k2. So yeah, that's just the recurrence if t would be equal to 2. Okay. Now, what we expect the time complexity of this to be? If assume that every single node n k 2. Oh, so Timur already knows. That's very nice. Yeah, a very naive analysis of this complexity would be that we have a 4 up to basically n, a 4 up to another k, and because we have to do this for every single node in every single subtree, we would have O of n times n squared, which is O of n third, which is not good for n equals 10,000. Technically, this is like n choose 2, but it doesn't matter. Complexity factors do not matter. But instead, let's better analyze what actually happens here. So I've written this pretty poorly. Let's assume that it's done from k. We fix k2 and k1, and then k is their sum, which is what I intended to do initially. Actually, for how what is the maximum value that k2 can take? in this case? Well, we can eliminate out of the subtree of S2 as many nodes as S2 has in its subtree. So we'll call this the area of subtree, of the subtree. So up to that value, that is actually the maximum value that K2 can take, because we cannot eliminate more nodes than there are in the subtree. Similarly, for S1, we will find that we can eliminate up to area of S1 nodes. Then what we really have, if the tree that we have is binary, is the sum of for every node, area of the left sum times the area of the right sum. We will make a bijection from this to the following set. So consider basically every single node that is here, which is A1, and then let's pair them with a node from A2. Then what actually are we counting here? We're actually counting the number of pairs U and V such that their LCA is actually this fixed node. So then if we were to instead iterate for every node for U, then for V, and add the frequency of, add a value to their LCA, the final value that we would have in this array F would be actually area of the left sum times the area of the right sum. And we know that since then this frequency array would be equal to the values that we sum here, that the sum of the nodes here will be equal to the sum of the values here. But here we add n squared values in total to this array F. So then this identity also has to be equal to n squared. So then the complexity, although at any point we might have such an iteration to take up to O of n squared for a single node, in total, it amortizes to O of n squared. Is that clear? Are there any questions? Okay, you might have noticed that earlier on I said, let's assume that t equals 2, and we basically solve the problem only for this, when we assume that t equals 2, because we just multiply the areas of the left sum and the right sum. But notice that, technically speaking, we can adapt this algorithm for any number of nodes, in fact. Wait, actually, I can just add a new image. Can I? I can. Whoa. That's so nice of them. Okay, good. So, how would we adapt this dynamic programming that we did for 2 nodes for multiple nodes? So we have dp of S1 K1 plus dp of S2 K2 goes into dp of node of K1 plus K2. I mentioned there is a +1. It's implementation details, whether you include it or not. Let's include it at the end for posterity. Then what actually happens here is that what technically is called max plus convolution. Because
we iterate through each index. We take the sum of the two values from either array, and then we take the maximum out of this. Some of you might have heard of FFT. FFT is technically a plus multiplication convolution, I think, in the same terms that this is defined as a max plus convolution. So a max plus convolution is when we construct an array C from two arrays A and I, such that C of I plus J is equal to the maximum of AI plus BJ. So I and J go to I plus J, and we take the maximum out of them. Then assume that we convoluted these two nodes. Basically, what we did here is called the knapsack, I think, in more familiar terms. It mimics a knapsack, almost. So assume that for these two nodes, we convoluted them and got like an array dp of S1 and S2. But essentially what do we want is to convolute every single dp of S1. So we have to multiply all of them. To actually be able to describe the partition of the count of undecided nodes to each of these subtrees. But obviously, if we don't have to do this in one single operation, we can convolute the byproducts one by one. So then we calculate the dp for only these two nodes. We calculate what is the maximum number of undecided nodes if we distribute only to these two nodes. Then we have a partial answer. If you were to distribute K1 to here, we will get so-and-so cost. Then we fix how many nodes we leave undecided in the third node, let it be K3. Then we have a DP where we take into account a distribution of undecided nodes, both to the first, the second, and the third node. So essentially, we do the n-squared algorithm for all of the pairs of nodes. Like we start with a prefix, and then we extend that prefix by applying the n-squared algorithm to combine that prefix with the next node. Okay. Similarly, because the what is the time complexity here? It would be area of S1 times area of S2 plus area of S1 plus area of S2 times area of S3, and so on. But this identity is actually the same that we discussed earlier, because still, if we consider any pair of two nodes, one of which belongs to one of the subtrees here, and one that belongs to some different subtree of this node, then technically this single pair will be counted at one point during this summation, when we take, essentially when we take the prefix of these nodes, and then we multiply it by the area of the subtree this node belongs in. So then again, what the complexity does here is to calculate pairs of nodes such that they have the LCA equal to node, which obviously the number of pairs of nodes in a single tree is n squared, because take any node, then any other node. So that is it basically. So what happened was we described the problem. I'll go over it again. We described the problem. We noticed that there is a DP formulation for it. We might have assumed wrongly that it may be solved in O to the third, but because we analyzed the complexity, by injecting the sum that we are actually calculating to the count of pairs of nodes, we notice that this dp is actually in O of n squared. Is that good? Are there any questions? Because I understand I should end now. I will share an implementation of this trick in the chat later. If there are no more questions, I apologize for the shorter lesson today, and we should see each other tomorrow. Goodbye.